Let's investigate the current global wealth distribution. A heavily researched area, there are many research papers which already exist on the current global wealth distribution. These papers agree on an overarching theme, that distribution of wealth follows an exponential distribution for the majority of the population, the non-ultra-wealthy, and changes to a power law distribution for the ultra-wealthy. What does this look like? Let's get some data points and see for ourselves. Before working with these functions, we need a brief overview of the exponential and power law functions. An exponential function has the general form a plus b e to the cx, with variables a, b, and c. Letting a equal 0, b equal 1, and c equal 1 gives the natural exponential function. Increasing the a value shifts the function up, and decreasing shifts the function down. Zooming out, we see that the horizontal part of the curve approaches the a value, here -2. Increasing the b value scales or stretches the function vertically. Decreasing shrinks the function until we get to negative values, which flip the function over the line y equal a. Here a is 0, so it flips over the x-axis. The c value is the growth or decay rate of the function. Growth for positive c values and growing faster for larger c values, and decay for negative c values, decaying faster as c gets more negative. The other function we're investigating is the power law function, with general form kx to the power d. K is the coefficient. Increasing k stretches the graph vertically, while decreasing k compresses the graph until we get to negative values where the graph is reflected about the x-axis. D is the power. The graph takes on many shapes depending on d. For our purposes, observe the vertical asymptote appears at x equals 0 for negative d values. Now, let's get some data points and try to find a curve modeling global wealth distribution. First, we study wealth distribution for the majority of the world, the non-ultra-wealthy. This graphic from the World Inequality Lab gives data points for every 10th percentile of individual net worth. The data is in euros. We'll convert into US dollars for this video, and the data is as of 2022. The ultra-wealthy could be considered the top 1%, the top 0.1%, or even smaller. However it's defined, the non-ultra-wealthy consists of at least all the bars outside of the top, which goes off the charts. So if the 8 billion people in the world in 2022 were listed in descending order of net worth, the 800 millionth has net worth 119,000 euros, roughly $140,000. The 1.6 billionth wealthiest at the 20% mark has net worth 53,000 euros, or roughly $62,000. And then all the way to the 90% point, which would give us the 7.2 billionth wealthiest person, would have a net worth of 330 euros, or roughly $387. There's a bit of an outlier at the far end of the graph, as the 8 billionth wealthiest, or least wealthy, has a negative net worth, looking to be roughly -40,000 euros. Neither the power law nor exponential function exhibits this behavior of sudden sharp decrease. A different distribution would be required to describe the wealth of this far end of the graph, the ultra non-wealthy, just as a different distribution is required to describe the wealth distribution at the ultra-wealthy end of the graph. So we will omit this ultra non-wealthy data point for studying the distribution of wealth for the non-ultra wealthy. Here, I've copied the data points from the World Inequality Lab onto an online graphing calculator. So at the 10% point, we have a net worth of roughly $140,000. At the 20% point, we have a net worth of roughly $62,000. And at the 90% point, we have a net worth of roughly $387. Now that we have data points, we can use an online curve fitter to fit both an exponential and a power law curve to our data. Immediately, we see that the exponential has a higher r-squared value. The r-squared measures how well the curve fits the data, so this supports exponential distribution, better explaining global wealth distribution for the non-ultra-wealthy than the power law. In blue, we have the exponential curve fit to the data points, and in red, we have the power law curve fit to the data points. Focusing on the exponential curve first, we see that all points are fairly close to the curve. Doing the same for the power law curve shows that the higher net worth points are close, but the lower net worth points are significantly further. Looking at a particular data point, we see that for the 80th percentile, while the exponential curve overestimates by a factor of about 2, the power law curve overestimates by a factor of about 4.5. So the exponential curve looks better for modeling wealth distribution of the non-ultra wealthy. How would it do for predicting the ultra wealthy? We can intersect the exponential curve with the y-axis to show how much the richest person in the world would be expected to have if the whole world followed an exponential distribution of wealth. As we see, this curve expects the richest person in the world to have $286,000. Adjusting for inflation from 2022 to 2025 doesn't really make a difference, as the richest person in the world would still only have $322,000. This is wildly inaccurate by many magnitudes. As of December 1st, 2025, Forbes lists Elon Musk as the richest in the world with a net worth of $482.5 billion. That means the exponential distribution gives a prediction 1.5 million times off. So while most of the world follows one distribution, extreme inequality allows the ultra-wealthy to not only reach a new stratosphere of wealth, but require their own wealth distribution. So the extreme inequality in the world can be characterized not only by immense wealth at the top, but by the ultra-wealthy needing their own wealth distribution. On this same graph, I've listed the top 20 wealthiest in the world according to Forbes. But we need to adjust our x-axis scaling, as before we looked at a range covering 8 billion people, and now we're looking at a range covering only 20. So number 1, we have Elon Musk with $482.5 billion. Number 2, we have Larry Page with $262.2 billion. And at number 17, we have Michael Bloomberg with $109.4 billion. And just as before, an online curve fitter fits both an exponential and power law curve to the data. The exponential curve has an r-squared value of 0.8994, while the power law has an r-squared value of 0.949, supporting the power law curve fitting the data better. These data points are much more volatile than the data points describing the wealth for the non-ultra wealthy, meaning the r-squared values corresponding to the curves for the ultra wealthy are much more subject to change. But we will soon see why, regardless, the power law distribution is much better at describing wealth for the ultra wealthy. So in blue, we have the exponential curve fit to the data, and in red, we have the power law curve fit to the data. Visually, the power law curve goes through the points much closer than the exponential curve. So, a power law distribution models wealth distribution for the ultra wealthy better than an exponential distribution. The power law curve massively overestimates the wealth for the rest of the world. The 10th percent should be 140,000, but is instead 19 million. The 50th percent should be 14,000, but is instead 8.6 million. And the 90th percent, who should be the poorest people in the world, now have a net worth of $6.5 million if the power law curve would describe the net worth for the majority of people in addition to the ultra wealthy. And note this blue line from the exponential curve, sitting at about $112 billion. This is a value which the function can never go below, giving some insight as to why the exponential function doesn't work as well for modeling the wealth distribution of the ultra wealthy, because the growth of the exponential function simply isn't as steep as the current wealth distribution of the ultra wealthy requires, whereas the power law function approaches the y-axis asymptotically. This is why we cannot say that the world follows one wealth distribution. It is more accurate to say the distribution of wealth follows a power law distribution for the ultra wealthy and an exponential distribution for the rest of the world. The necessity for different functions explaining the distribution of wealth for the ultra wealthy versus the rest of the world acts as strong evidence that the game of wealth accumulation is inherently unfair, supporting that capitalism as a political economic system lets the ultra wealthy play by different rules than the rules played by everyone else.